Okay, let's start. So today we are going to talk about surface area and surface integral of functions. Next time we will talk about the surface integral of vector fields. So surface area and surface integrals of functions. So first, so suppose we have a surface in 3D. So take coordinates x, y, z, and so let's draw a fancy picture. And this is your surface. Okay, let's call it S. Last time we talked about parametrization of surfaces in 3D, and here we suppose the yellow surface S has a parametrization by something in 2D. For example, take a UV coordinate, and here you have some kind of domain R, such that this is a parametrization gamma. UV is a parametrization. Now we want to compute, so the question is, what is the surface area of S? So as what we did before, we first do some infinitesimal approximation of the area, and then we use Riemann sum to sum them up, finally take the limits to write down the sum as an integral. So here we first interested in the following small cube. So suppose here you have some grid along U direction and along V direction. And in particular, we are interested in this small cube. And correspondingly, here you will have some small curved surface here. So they are one-to-one correspond to each other. And if we write down the coordinates, then on this side, let's write more clearly. Enlarge it. Here you will have U0, V0, U0 plus du, V0, U0 plus du, V0 plus dV, U0, V0 plus dV. And then on this side, you might have curved one. And I'm sorry. Oh yeah, you should have green one. And here you have gamma U0 plus gamma U0 V0, gamma U0 plus U0 V0 plus dV, gamma U0 plus du V0 plus dV, gamma U0 plus du V0. Okay, now so what we are interested actually on the right hand side, we want to compute the area for this curved thing, and then we do a linear approximation. So linear approximation by some parallelogram. So what will be the parallelogram? So the four vertices are determined by the linear approximation for gamma. In other words, on this side, you have gamma u0, v0, and on this vertex is given by the linear approximation. So gamma u0, v0 plus dv is approximately equals gamma u0, v0 plus gamma v u0, v0 dot dv. And also this right lower corner, gamma u0 plus du v0 approximately equals to gamma u0 v0 plus gamma u u0 v0 du. Okay, then what is the area? So the area, we first finish with the right hand side and then we go back to the left hand side. So the area of the parallelogram is equals to, let's see, so this vector cross product this vector and then take the norm. So we will have this equals to gamma. So let's use the black one. Gamma u u0 v0 du cross gamma v u0 v0 dv. And if you factor out the du dv, then you have gamma u cross gamma v du dv. Of course, here you evaluate at u0 v0. Okay, now we go back to the left hand side. So remember, so this is actually equals to gamma u cross gamma v, which is a function on u and v, and dot area for the green box. Okay, now the area for the whole surface S is approximately, if you do the cutting here, so you also do cutting on this side, small pieces, then we have the following approximation as Riemann sums. This will be equal to summation of the area of the small curved one, gamma ij. And then this, by the previous formula, this is approximately equal to area for the parallelogram. And for the parallelogram, we computed this equals to gamma u cross gamma v dot area of the green box. Sorry, here you have summation. Here you also have summation. Oh, sorry, the summation is outside. Okay, so what is this guy? So if you take the limit, this is just approximately equal to the integral over the whole region R. So over the whole region R of the function gamma u cross gamma v dA. Okay, so the conclusion as a conclusion, we have the following formula. The area of S is given by the integral of cross product of partials of the parameterized domain R. Okay, now before we talk about the surface area of functions, we compute some example. So example 1, let's consider the surface area of x squared plus y squared plus z squared equals a squared. Of course, you noted that this is a surface, so the surface area can be computed by the formula 4 pi r squared, so here a squared. That's what you expect. Okay, now let's derive it explicitly. So first, take the following parameterization. So x is a sine phi cosine theta, y is a sine phi sine theta, z is a cosine phi, and phi is between 0 and pi, theta is between 0 and 2 pi, just a spherical coordinate. And then we compute gamma. Here your variable is, notice that here a is a constant, so your variable is phi and theta. If you draw the picture, then here phi and theta, you have some box, go this way, and parameterize. A surface here, x, y, z. Okay, and then gamma phi. What is gamma phi? You take phi derivative is a cosine phi cosine theta, a cosine phi sine theta, negative a sine phi. Gamma theta is a sine phi, negative a sine phi sine theta, a sine phi cosine theta, 0. Okay, then let's do the cross product. This is I, J, K, a cosine, sorry, I should leave more space. A cosine phi cosine theta, a cosine phi sine theta, negative a sine phi, J, K, negative a sine phi sine theta, a sine phi cosine theta, 0. Expanded, you have I times a squared sine phi squared cosine theta minus j minus a sine phi times minus a sine phi sine theta plus k a squared sine phi cosine squared and plus sine theta sine squared. Okay, simplified, you have I a squared sine phi squared cosine theta plus j a squared sine phi squared sine theta plus k a squared sine phi cosine phi. Okay, now let's take the norm of gamma phi, gamma theta, the cross product between gamma phi, gamma theta. So this is square root a square sine phi square cosine theta square plus a square sine phi square sine theta square plus a square sine phi cosine phi square. So a little bit computation, you will have the answer is a square sine phi. Notice that because phi is between 0 and pi, so this a square sine phi is always non-negative, so you don't need to take care of the sign issue. Okay, next we plug into, remember our formula says area is given by the integral over r and a square sine phi dA. And this is a double integral. We just write down the domain and the coordinates. So since we have phi and theta, phi is between 0 and pi d phi, theta is 0 to pi d theta. So you have this guy, and you have 0 pi 2 pi a square sine phi d phi. So 2 pi a square negative cosine phi, pi and 0. You have 4 pi a square. That's what we expected. Okay, now let's generalize the surface area to surface integrals of functions easily. Because here, if we suppose you have S in 3D, so what is area of S? Just recall what we did in 2D. Recall. In 2D, so what is area of R? This is the double integral over R of the function 1, right? So here, the same thing. So the area of the surface S is expected to be some surface, although we don't have definition for surfaces. Surface integral of function 1 here, right? So that's what we expected. So if we change 1 to arbitrary functions, we have the definition for surface integrals of functions. Just like what we did here in domain 2D. This is double integral. For any function R. Okay, so this is the idea. So how to make this definition rigorously? We still need to use a parametrization. But the idea is very similar. Suppose you have parametrization R on this side, which parameterize the surface S on this side, and and then the one we want to define is, so suppose you have some function f, x, y, z in 3D. In particular, it has meaning on the surface S. So we want to define this one, and therefore we cut it into small pieces, ij, area called ij times function f x I j star y I j star z I j star. Here the cutting is given by the corresponding cutting in R domain or in UV domain. Okay, so suppose you have cutting on this side, and then you will have corresponding cutting on this side, just as what we did for area surfaces. Okay, and then for each one, you can approximate it and do an approximation. You will have this is area ij, the summation of area code when you can approximate by parallelogram, and then parallelogram. So let's do parallelogram, and everything else is the same. You still have f x I j star y I j star z I j star, and then for the parallelogram, you can transform it back to your R domain. So this is area for the green box. But you have an actual factor. So let me write down the actual factor. Gamma u cross gamma v. Okay, so this altogether is the same as area of the parallelogram, and then of course you have the information from function side. Okay, now we rewrite it. This is summation ij gamma u cross gamma v, take the norm, dot function information. And for the function, you write down in UV variables. So x, u, I, v, j, and y, u, I star, vj star, ui star, vj star, just by substitution, like what we did before, uj star. Okay, and then you have area dot area, this part, which is du dv. So okay, I will keep it like this. And then again, you by approximation, this is just a double integral over R of the function f x u v y u v z u v gamma u cross gamma v dA. So it's a double integral of the function and some substitution, and with an actual factor, gamma u cross gamma v norm. Okay, and so there's a definition of surface integrals of functions just given by, so here left hand side is the notation, ds. So here S, it's a capital S, means the surface area element defined to be double integral over R f x u v y u v z u v z u v norm gamma u cross gamma v dA. Okay, so that's the definition. Actually, that's a way to compute this one. Most of the time, you use the right hand side to compute the right hand side, the left hand side. And let's discuss some easy case. Suppose you have graph, then you can simplify the above definition or formula a little bit. So suppose your surface is given by x, y, g, x, y. And then here, of course, x, y are nature parameter for your surface. Then gamma x cross gamma y is given by I, j, k. And gamma take x derivative is 1, 0, gx. And gamma take y derivative is 0, 1, gy. And then you have I negative gx minus j gy plus k, or in vector form, or in coordinates, you have negative gx, negative gy, 1. Therefore, the actual factor can be computed by square root gx squared plus gy squared plus 1. And then the surface integral is given by f times, of course, you need to transform to, okay, so let me just write down gxy. And then you have actual factor gx squared plus gy squared plus 1 dx dy. If you don't remember the formula, it's okay. So just use the original one and to deduce that. If you remember, you can just apply it. Actually, this guy is just similar to the length of curve, because they're just infinitesimal version of Pythagorean theorem. Or you can see Pythagorean theorem. Okay, now let's carry out one example of how to compute the surface integral of a function for, at least for a graph. So, example. So suppose we want to compute surface integral of function z over surface S, where S is the surface whose sides S1 are given by the cylinder x squared plus y squared equals 1, whose bottom S2 is the disk in the xy plane. In other words, the z coordinate is 0. and the top S3 is the part of the plane z equals 1 plus x that lies above S2. So let's draw the picture. So suppose you have XYZ. And then the bottom you have S2, so it's a disk. Okay, and then sides, just cylinder. This is sides. And then the top, given by this one. So the equation is, what is the equation? Z equals 1 plus x. Z equals 1 plus. Yeah, I give the wrong coordinates. Probably I will adapt it a little bit. Z equals 1 plus x. Yeah, probably this is y. This is x. And this is y. Okay, then it's okay. I hope so. Okay, next, because later on, this picture just for illustrating. So later on, everything we computed based on explicit formula. So as soon as you get the idea, it doesn't really matter if you make some mistake when you do drawing. But of course, it's better to have correct picture. Okay, now, as this picture indicates, you have 3 different parts. S1, also this is S1. S2 is bottom S3. Okay, then we compute them separately. So for the S1 part, so S2 part is the easiest, because you notice that since z equals 0 on the disk, x squared plus y squared less than 1 on xy plane, then the surface integral just integration of 0, which is 0. Okay, for S1, then you notice we should use cylindrical coordinates. So so in other words, in this case, the r is 1. Then we have the coordinates. X is r cosine theta, so cosine theta. Y is r sine theta. Z is z. Okay, next we need to figure out parametrization on this side, such that on the right-hand side, you have the you have S2. Okay, and now we look at the equation because you have two equations. First, z is greater than 0. So notice that because it's above the xy plane, so z is always bigger than 0. And on the other hand, it's below z equals 1 plus x, so this is less than 1 plus x. Okay, and then the parametrization, theta has a natural region between 0 and 2 pi. Therefore, on the left-hand side, you will have, suppose this is your theta, this is your z, and okay, so let's change a little bit because now x is not a variable. So you change it to z greater than 0, z less than 1 plus cosine theta. Or z is between 0 less than 1 plus cosine theta. Just like you had two boundaries. And now your theta is between 0 and 2 pi. And z is between 1 and cosine theta. So you expect when theta is 0, you have 2. And when theta is pi, you have 0. When theta is 2 pi, you have 2 again. So this will be our picture. Okay, so this is parametrization R2, which parameterize our S2. Okay, now everything is clear by the formula. So the surface integral of z ds2 ds by the formula can be computed by integral of r, and the function is z. Z is just because z is our parameter, so you keep z here, and then actual factor, this is gamma theta cross gamma z and dA. Now let's compute gamma theta cross gamma z. So cross product ijk because of the parameterization is here. So you have negative sign, cosine 0, 0, 0, 1. So finally you have cosine theta plus j sine theta. So gamma theta cross gamma z take the norm, just 1. Okay, therefore the surface integral over S2 of z is double integral over r of z dA. And now our domain is type 1. You have two boundaries. Also boundary. Okay, then you can write down as the following. So first, outside you do the theta integral, and then inside you have a z integral from 0 from 1 plus cosine theta. Inside you have z dz. Okay, then you just do iterative integrals. 1 plus cosine theta squared over 2. And then let's distribute and do triangle formula 0 to pi and 1 plus 2 cosine theta plus 2 cosine 2 theta plus 1 over 2, okay, d theta. Therefore, you have 1 over 4 theta minus 2 sine theta plus 1/2 theta minus 4, oh sorry, here plus sine 2 theta 2 pi to 0. And then if you evaluate, you will have 1/4 times 3 2/2 times 2 pi 3 pi. Do I make mistake? Oh yeah, so here this is 2, so when you factor out you should have 2 here. Two. Okay, so this is S2. Now let's do S3. So recall, here we recall the S3 is given by the function z equals 1 plus x, and if we parameterize by r and theta, we can have the following. So actually here you can split it into 2 parts. So first view it as a graph, 1 plus x. Step 1. And then step 2 for xy, because xy gives you a disk region, so you parameterize by polar coordinates. So you have r cosine theta, r sine theta, 1 plus r cosine theta. That's how you decide your parameterization. So x is r cosine, y is r sine, z is 1 plus r cosine theta. And of course, theta is between 0 and 2 pi, r is between 0 and 1. Now let's compute the cross product. So you take r derivative, you have cosine, sine, cosine. You take theta derivative, you have negative r sine, r cosine, negative r sine. Okay, then for I, you have negative r sine square minus r cosine square, negative r, and then minus j. Then for j, you just have 0. And then for k, you have r cosine square plus r sine square, which is r. So the norm of this cross product is square root r square plus r negative r square plus r square, which is square root 2r. Okay, now you plug into your formula. You have the following: integration from 0 to 2 pi, and then integration from 0 to 1. The function z is 1 plus r cosine theta, and then the norm of the cross product gives you square root 2r, and then you have dr d theta. Okay, and then you can first do the r integral, which gives you square root r squared over 2 plus square root cosine theta r cubed over 3, 1 to 0 d theta. And then you plug in, you have square root 2 over 2 plus square root 2 cosine theta over 3, integration from 0 to 2 pi d theta. So it gives you square root 2 theta minus plus square root 2 square 3 sine theta evaluated at 2 pi and 0, which gives you square root 2 pi over 2 times, square root 2 over 2 times 2 pi, which gives you square root 2 pi. Okay, then let's sum them up. The integral over the whole surface S is given by the summation of three small integrals S1, S2, S3, and each one we computed as above. So we just write down the answer here: square root 2 pi plus 3 over 2 pi and square root 2 pi. So finally 3 over 2 plus square root 2 pi. Okay, so we stop here. Next time we will talk about the surface integrals of vector fields.